Hello, this is the PBL of Ana Karen, Erika, Raúl, and Miranda. Why in the majority of the arteries, when they divide, they do it as a bifurcation instead of a trifurcation? I guess that is how to do something with the units of energy and power. But how I relate these values with fluids and pressure? First of all, we're going to start defining some terms of the problem. Energy is the ability to do work, and there are two types of energy, the kinetic energy and the potential energy. The kinetic energy is the one that exists due to the motion of an object, and this is a formula. And the potential energy is the one that is stored in an object due to its position and height, and this is. And the joules of energy are, the units of energy are joules or newtons meter. And the equation has the law of conservation of energy. Then, power is the rate of doing work or of transferring heat, and the amount of energy transferred or converted per unit of time. That is also a definition of work, and its main unit is watt. Here is the formula of power, and also we can take work over time. So pressure in a fluid can be seen to be a measure of energy per unit volume, or better known as energy density. This energy is related to other forms of fluid energy by the Bernoulli equation, and pressure can be defined as energy over volume. An application is to the hydrostatic pressure of a fluid, where pressure can be used as energy density alongside kinetic energy density and potential energy density in the Bernoulli equation. So here we can notice the hydrostatic pressure and the kinetic and potential. About the Bernoulli equation, it is a statement of conservation of energy principle appropriate for flowing fluids. And we can see how in this narrowing we have an increased fluid speed but a decrease in pressure. So this is the equation that relates point 1 and point 2 and has pressure energy, kinetic energy, and potential energy, and always taking into account the conservation of energy.
Now, as seen in the image, an artery bifurcation is when the artery divides into two sections. We can see it in the following image with the abdominal aorta, which divides in the aortic bifurcation to be later the common iliac artery, the internal iliac artery, and the external iliac artery. In this image, we can see the cross-sectional areas of the bifurcations from the beginning towards the end. The flow in these bifurcations depends much on the geometry, flow division, the inflow conditions, the flow path curvatures, as well as the changes in the cross-sectional areas. What will also depend are the secondary flow patterns, and these will be affected rapidly in the increase of the cross-sectional area that produces changes in pressure, as well as the near-wall velocity. This secondary flow will increase strength when the angle of the bifurcation is obtuse. Therefore, this one. In the following image, we can see that the velocity profile changes when there is a flow division. Thus, here and here. The wall shear stresses will be much higher at the flow divider wall than at the outer walls. Here, we can see an image that demonstrates the fluid dynamics of flow in the bifurcation. Here we can see that we're going to find a low wall with shear stress. The flow divider will be here. Here we're going to have a wall with high shear stress, as well as on the other side of the bifurcation. And here we're going to have another low side. And this is part of this image, where we can see that at the inner wall there is a high value, whereas in the outer wall there is a low value. Now, for general fluid mechanic considerations, we have to take into account the fact that the cardiovascular system functions with an unsteady or a pulsatile flow due to the beating of the heart. So, in most analysis of this system, we have to include a local acceleration term. Another thing to consider is the Reynolds number, which can range from 1 in very small arterioles to 4,000 in very large arteries. And in these very small ones, the viscous forces are going to be dominant, whereas in the arteries with a large Reynolds number, the inertial forces are going to dominate. Another important number is the Womersley parameter. This is basically the ratio of the unsteady forces to the viscous forces, and it's defined as the following equation, where alpha is equal to r, which is the tube radius, times the square root of w, the angular frequency, divided by v, the kinematic velocity. And this is obtained by the dimensional analysis of the Navier-Stokes equations. Basically, when there is a low alpha, the viscous forces will dominate and the velocity profiles are going to be parabolic in shape. And the centerline velocity oscillates in phase with this driving pressure gradient, whereas when alpha is greater than 10, as for example seen here, the unsteady inertial forces are going to dominate and flow is going to be like a piston. Basically, the amplitude of this motion will decrease at higher frequencies, and there is a 90-degree phase difference between the pressure gradient and the flow. In this image, we can see this example further. Here, shown in blue, the graph shows the pressure gradient of a cosine function, and the other graphs show dimensionless velocity profiles for different Womersley numbers. So, as we defined earlier, for low Womersley parameters, we're going to have this parabolic shape, whereas when the number gets bigger, such as here, 16, it's going to be this piston-like motion. Lastly, we're going to give this example of the carotid artery bifurcation. This artery has a mean Reynolds number of 300 with a Womersley parameter of 4, and the branches are about at 25 degrees off the axis of the parent artery. So basically, with this Womersley parameter, we can predict that there's going to be a parabolic profile. Other things to consider are that the axial velocity profile in the sinus region of a 3D model, for example here, they were obtained through laser anemometry and computational fluid dynamics. So we can see the radius being compared to the axial velocity, and in these images to the bottom, we're going to be seeing the flow in the carotid sinus. It's unsteady with a transient reverse flow in the outer wall, and in this 3D plot, we're going to see the velocity versus the diameter, position, and time.